we're going to construct an unscaled sine curve. We start with a circle, and center of the circle is going to be the origin of an XY coordinate system. We start from the positive x-axis, and we make a series of equally spaced points around the circle. Now, I'm not going to be very successful at actually spacing these points equally. I could be more careful and probably do a pretty good job of this, but let's just say that these represent equally spaced points. Now, how many do we have? 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5 here, 3, 4, 5, 6 here. These are bunched up a little bit. Of course, that arc is lopsided. 1, 2, 3, 4, 5. Okay, so they don't form a perfect series of equally spaced points, but we're going to pretend they do. So for each point, I'm going to sketch a vector, just an arrow from the x-axis straight to the point on the circle. Now I'm going to go off camera and draw the rest of them. You should probably draw this yourself and complete the thing before I come back. Okay, not a great picture, but I'm just kind of slopping this down, and I recommend you kind of do the same thing. Obviously, I'm vertically challenged. This isn't parallel to this. All these should be perfectly vertical, parallel to the y-axis, which should be a perfect right angle with the x-axis, and so forth. In any case, I've got a series of arrows around the circle. And now, what I want to do is I want to create a graph. I want my horizontal axis to be marked off with an equal number of points. So I'm going to do that. Points should be equally spaced. Don't know if I managed that. Now, first point's going to correspond here. The arrow to this point would have length 0 because, of course, this point's right on the x-axis. The second point, though, we would draw an arrow here. And for the third point, we might draw an arrow here. For the fourth point, an arrow here. And for the fifth point, and the sixth point, and so forth. So I could draw a series of arrows mimicking these arrows. So here we have our picture where we've taken these arrows in order and sketched them in the vertical direction at successive equally spaced points on the x-axis. And the number I've got here, the number of arrows I've got here, I don't think matches the number of arrows I have on the picture. If you did this, you should try to do it a little more carefully, but we get the idea. Now, the length of each arrow is the y-coordinate of the point, and we could project each point over to the y-axis, and we could get a set of y-coordinates which would match the y-coordinates that we might get here. And of course then we can also sketch a smooth curve through the tips of these arrows so that the x-coordinate represents, to some scale, how far we've moved along the arc of the circle, and the y-coordinate, of course, represents the lengths of these arrows, or the y-coordinates of these points. And this is what we're going to call an unscaled sine curve. Now, we can scale the curve. There's no scale on this curve. We don't know how far this is. There's no labeling of the graph at this point, and nor is there any labeling of the y-coordinate or the vertical coordinate of the graph. These arrows are scale models of these arrows. These arrows obviously don't have exactly the same length as these arrows, but they represent the same length, just to a slightly different scale. Now, one way to scale this is assume the circle has a radius a. Then the tallest vector is going to have a height equal to the radius of the circle, or the vector that we would get if we had a vector right along the y-axis. We have a vector slightly to the right, a vector slightly to the left. They're a little bit shorter. The longest of the vectors that we could get would have length A. And we would have that here and here, giving us negative A and A as maximum and minimum coordinates. Now perhaps the most natural way to scale the horizontal axis is to scale it in terms of the arc distance S, the distance the point moves starting from here to get to a given point along the circle. To get all the way around the circle, which would correspond to the complete cycle of this function that ends here, how far would we have to go? Well, the circumference of the circle is 2 pi r. So that according to this labeling, this point will have coordinate 2 pi r. This point, of course, will be halfway. It'll have coordinate pi r. A point where the graph meets the minimum here is going to have 3 pi over 2 times r, and the point where we have the maximum is going to be at pi over 2 r. Another possible labeling is in terms of the angle theta. Theta being the angle through which we have to rotate this vector to move it from here along the positive x-axis to whatever the position happens to be on the curve. And you should understand, hopefully, and if you don't, you can see some of the subsequent videos where this is explained, but theta is measured in radians. Okay, now radian is a unitless quantity, so I'm not even going to indicate that theta is in radians. Theta is automatically in radians. If you want to measure it in terms of degrees or something else, you put a parenthesis here and put degrees or rotations or whatever you want to use. But the default for theta is radians, and to get the number of radians, we simply divide the distance we move along the arc by the radius, so that the number of radians is the number of radii we've moved along the arc. Now I realize that I've just done something. I've used r for the radius of the circle instead of a, and this should have been pi a and so forth. I'm going to correct that, and I'm going to add the labeling in terms of theta. Okay, now instead of multiples of r, we have multiples of a, which is the presumed radius of the circle, and when we divide the arc distance along the circle by the radius, we get the angles. Okay, these are in radians, but we don't have to write a unit when we have an angle in radians. Now we could also do these angles in degrees, and there could be some usefulness in that, but it's really counterproductive to do that in any course where you're solving certain types of problems, and especially in a calculus or analysis course. So I've cluttered the picture up a little bit with the labels in degrees, and these should be very obvious to you. So I have theta in degrees. And I'll do one other thing. Let's assume there's a revolution every 8/10 of a second. Then I could do time in seconds. And I didn't leave myself a lot of room down here, so I'm going to label up here. I'm going to put 0.8 here, and of course halfway is going to be 0.4. Halfway between here and here, at the minimum point, we're going to have 0.6, and over here where we reach the maximum, we're going to have 0.2. So now I have a labeling for time in seconds, and that could correspond to a very tangible occurrence. For example, we could have a weight oscillating up and down on a spring. This model, the y-coordinate on this model, can accurately model the motion or the position versus time of that weight on the spring. If that weight's taking 0.8 of a second for every oscillation, then if we have the right number for the radius of the circle, we can have a very good model for the motion of the weight on the spring. There's another way this weight on the spring can oscillate. Now actually this is a compound oscillation because you're getting a little up and down because of centripetal forces and so forth. But it can oscillate back and forth as a pendulum. And we can model that conveniently by looking at the x-coordinates of these points. The picture's getting a bit cluttered, but I started here and drew arrows in yellow to indicate the x-coordinate of each position. And I can continue that. And so forth around the circle. To create a graph, I can do something very similar to what I did here, except of course that on the vertical axis I'll be plotting the lengths of the vectors, so these vectors are going to turn around and go vertical, so that I still have a plot of whatever is represented here versus, let's say, time, if we're trying to model the back and forth motion of a pendulum. In this case, the first vector is this long, so that's going to be the vector of maximum length. That's going to correspond to the radius of the circle. And we draw that vector here, and then the vectors start decreasing in length, and then they start increasing in length after we pass through here, but in the negative direction. So we see what happens, and it should be fairly clear how this graph is constructed. So our graph might look like this, where A is here, negative A is here. I got a little exaggerated when I went below the axis, so my negative A looks bigger than my A, but drawn carefully, you understand what the graph would look like. And it could be labeled in every manner similar to this one. So the full cycle, if the pendulum also has a period of 0.8 seconds, would be 0.8 seconds, or 2 pi A, or 2 pi, meaning 2 pi radians, 360 degrees, or even, didn't label it over here because I didn't have a lot of room, I could label this as 1 revolution. And then the halfway point and the 3/4 and quarter-way points would be labeled similarly.